Have you ever stopped to think about molecules not just as, a bunch of letters and numbers on a page, but as tiny, intricate pieces of architecture? Seriously, each one has a specific 3D shape, a blueprint that totally defines what it does. And this architecture, well, it holds a pretty fascinating secret, a puzzle that's really at the heart of chemistry. So let's dive in.
And it all starts with this question. This puzzle, how is it even possible for two molecules, built from the exact same atoms, to act in completely different ways? I mean, one could be a life-saving drug, while its identical twin is totally useless, or maybe even dangerous. The secret, you see, isn't in the materials, it's in the blueprint.
Take lactic acid, for example. There are two versions of it. They have the exact same formula, C3H6O3, and they are perfect mirror images of each other. But here's the crazy part. When your muscles are really working hard during a workout, they only produce one of these forms. The other one, that's made by some bacteria. So same parts, but our bodies can instantly tell the difference. This puzzle is the whole point of a field we call stereochemistry.
To really get this, we need to see what the architects, the chemists, see. We've got to look at their blueprints. Now, the big challenge is always, how do you show a 3D building on a flat 2D piece of paper or a screen? Well, to solve that, chemists came up with a few really clever ways to draw them out.
Okay, first up is the wedge dash projection. You should think of this one as the classic 3D drawing. The solid wedges, those are the bonds that are popping out of the screen, coming right at you. And the dashed lines, those are the bonds fading into the background. It gives you a really immediate sense of the molecule's actual shape and depth. But what if you don't really need that whole 3D look? What if you just want a simple flat view so you can compare things quickly? That's where the Fisher projection comes in. It basically squashes the molecule into a 2D cross. The horizontal lines are treated like they're coming towards you, and the vertical lines are going away. It's not super realistic, I'll admit, but it is incredibly useful for quickly comparing the layouts of similar molecules side by side.
Now, the sawhorse projection gives us a totally different perspective. It's like we're stepping off to the side and looking at the molecule from a slight angle. This view is fantastic for seeing how atoms on neighboring carbons relate to each other, whether they're staggered and stable or eclipsed and kind of bumping into each other.
And last but not least, the Newman projection. This one might be my favorite. With this one, you are looking straight down the barrel of a carbon-carbon bond. The front carbon is just a dot, and the carbon in the back is a circle behind it. This blueprint is absolutely perfect for seeing how the groups rotate around that bond and for figuring out the most stable arrangement. So there you have it. 4 blueprints, each one showing us the same 3D reality, just from a different angle.
All right, now that we have our blueprints, let's get back to the puzzle. We're talking about isomers. These are molecules built from the exact same set of materials, the same atoms, but somehow they end up as completely different buildings.
So let's just put a formal definition on it real quick. Isomers are simply compounds that share the same molecular formula but have different structures. And because of that, they have different properties. It is all about how the atoms are arranged.
Now, this puzzle really breaks down into 2 main types. On one side, you've got structural isomers. This is like having the same pile of bricks and wood, but one person builds a bungalow and another person builds a 2-story house. The atoms are connected in a completely different order. But on the other side, you have stereoisomers, and this is where it gets interesting. Here, the connections are all identical. It's the same floor plan, but the 3D spatial arrangement is different. Think of it like having the door on the left wall instead of the right.
So for the rest of this explainer, we're going to focus in on those stereoisomers, because that's where the most subtle and, honestly, the most fascinating architectural differences are. This is the real heart of stereochemistry.
And inside this world of stereoisomers, there are 2 main players we really need to get to know. First, you've got geometrical isomers, which you might already know as cis-trans isomers, and second, there are optical isomers, which are also called enantiomers. Geometrical isomerism happens when there's a rigid part of a molecule, like a carbon-carbon double bond, that can't rotate freely. It's locked in place. This creates 2 very distinct possibilities. If the important groups are on the same side of that double bond, we call it the cis isomer. If they're on opposite sides, it's the trans isomer. It's a simple flip, but it can totally change the molecule's shape and its properties.
And this brings us right back to our lactic acid mystery. Optical isomers, or enantiomers, are molecules that are perfect, non-superimposable mirror images of each other. And the classic analogy for this is perfect. Your hands. Your left hand and your right hand are mirror images, right? But no matter how you twist and turn them, you can never get them to line up perfectly. Well, molecules can have this same exact-handedness, and it's a profoundly important property, especially in biology, where shape is everything.
So,
We've got these amazing molecular buildings, but what happens when chemists want to, well, change them? They perform chemical reactions. We can think of these as molecular renovation projects, totally transforming one structure into another.
Now, there are tons of types of renovations, but 3 of them are super common. Substitution is just like swapping out an old window for a new one. Addition is like building an extension onto your house, adding new atoms across the double bond. And elimination is the exact opposite. It's like knocking down a wall to open up a room, removing atoms to create a double bond.
So let's zoom in on that first project, substitution. When chemists want to swap one piece of a molecule for another, it turns out there are 2 main ways the construction crew can get the job done. These 2 renovation plans are called SN1 and SN2. The SN2 reaction is a really swift, one-step process. The new group comes in and attacks, kicking the old one out all at the same time. The SN1 reaction, on the other hand, is a more patient 2-step deal. First, the old group just leaves on its own, which creates this unstable intermediate thing. Then, the new group comes in to fill the empty spot. 1 step versus 2, a totally fundamental difference in strategy.
And this table here, it just lays out the key differences perfectly. As you can see, SN1 is 2 steps, and it involves something called a carbocation intermediate. It works best on more crowded carbons. Those tertiary ones are the fastest. SN2 is just a single step with no intermediate at all. It needs an open, uncrowded space to work, so it's fastest on the least crowded primary carbons. They're pretty much opposites in how they work and the conditions they like.
You know, this brings us full circle, and it just perfectly captures the whole point of everything we've talked about. You can stare at a molecular formula all day long, but you're just not going to see the crucial differences. You have to think in 3D. The secret really is in the architecture.
So, if molecules are buildings and chemical reactions are the renovations, well, this simple idea leaves us with a pretty fascinating final thought. As our understanding of this 3D architecture gets more and more sophisticated, what incredible new structures, new medicines, new materials, new technologies are chemists on the verge of designing and building for us next?